well, let's get started because we also have a quiz today. So I have a couple of announcements. Hopefully you got the announcement on Canvas about the problem session today. So it will be today from 4 to 5 p.m. I didn't send out another announcement. Okay, well, the problem session will be today. So it will be held on Mondays, 4 to 5 p.m. It is optional. I will post the worksheet so all the problems that I'm going to have you guys work on. And if you can't make it to the problem session, you can still look at the problems. The benefit of going to the session is that the TAs will be there and you'll be able to ask questions. And you can also ask questions about stuff from in class or anything like that. So that's something to keep in mind. If you can't make it to this time and you really wanted to, you can let me know and I'll try and work something out. Like if you really wanted to go to the problem session, but this was the time that worked for the most number of people. Of course, not everyone can make it at every time, so it's difficult to find a good time. The other thing I was going to say is that I forgot to post the homework yesterday. So the homework for this week will be posted today. And I believe that we'll keep it consistent. So it'll be due on Saturday. Okay. Other than that, let's get started. So we are in section 1. What section are we in? I don't know what the section is. 1.5, I believe. Right. Let me check what is the name of this section? Okay. Oh, doesn't want to let me look at the textbook. Okay, well, where are we now? We're in section 1.5 and we're going to start talking, I think it's called solution sets actually. I'm not entirely sure about this, but something like this. So we are going to be talking about solutions to first homogeneous equations. So the first thing that we're going to define is a homogeneous equation, right? So, or sorry, a homogeneous system of equations. Right? And this is a system of the form ax equals 0, right? So this is our standard equation is, or how we were expressing it was ax equals b, right? So in this case, we're just b is equal to 0. So this is a system of equations. We're representing it using a matrix because it's the most compact way of writing it. So that's nice. And it's just equal to the 0 vector, right? So on the right-hand side, we have 0. Something special about this, so this type of system is always consistent. And that is because x equals 0, the 0 vector, is always a solution. So because whatever a might be, if we multiply it by 0, the 0 vector, we just get the 0 vector, right? So that is always a solution. It actually has a special name, and it is called, so the solution x equals the 0 vector is called the trivial solution. Okay. So far we have homogeneous and trivial solution. Those are our two terms we've defined so far. Okay. So we know that this is always a solution for any homogeneous system of equations. So we're sort of not that interested in this particular solution, right? We're more interested in non-trivial solutions. So so this is how I abbreviate solutions. I know it's kind of strange, but so SOLN is solution. Okay. So non-trivial solutions of homogeneous systems. Here is a fact. Look, when we're looking at a homogeneous system of equations like this has a non-trivial solution. If and only if the equation has at least one free variable. Okay, so this is a fact. Let's think about why this might be true. So why is this true? Well, first let's notice for a homogeneous system of equations, if it has any non-trivial solution, so anything other than x equals the 0 vector, if it has any non-trivial, solution, it will not be unique. So this is because if we have a unique solution, then we only have one, right? So we go from that single unique solution. If we have a non-trivial solution, we have to have infinitely many solutions. So this is that thing that we talked about at the beginning. You either have one solution or you have infinitely many or you're inconsistent. Now we know that a homogeneous system is always consistent. We always have at least one. So if we have any non-trivial solutions, we have infinitely many, right? Which means we have infinitely many. Oops. Let's see. Okay, so now thinking about this again, this fact, if the equation or this system, sorry, I guess matrix equation, but if this system has infinitely many solutions, then the equation has to have at least one free variable. Or is that how I want to say this? Yeah, that's fine. Or system. Okay, that part is that part clear for everybody? So if we have infinitely many solutions, we should have a free variable. Okay, so if there's no questions, I'll assume that this makes sense. And going the other way, so similarly, if the equation has a free variable, so if x equals 0 has a free variable, then it has infinitely many solutions. And we know this because when we have a free variable, that's how we are able to write down the general solution with a parameter and see that we have infinitely many solutions because we have one for each value of that parameter, right? So if it has infinitely many solutions, that means it must have a non-trivial solution. Okay, so we've shown that if we have a non-trivial solution, the equation has at least one free variable. If the equation has at least one free variable, this matrix equation has a non-trivial solution, or the system has a non-trivial solution. So we've shown one implies the other, and then the other implies the first one, right? So we have an if and only if. Okay, so this is going to be a useful thing to have, this fact. Okay, now let's talk about how we might write down the general solution of a homogeneous equation. So it will be a little bit different than how we've been writing down general solutions because now we have this idea of a vector equation, and that's going to help us write it down in a way that will be, I mean, in my opinion, I think it's nicer. It's a nicer way of writing it down. It's a little bit easier to see what the solution set is going to look like, okay? So writing down the general solution of a homogeneous equation, but really you could do this for any system. So of a system. And this is going to be in parametric form. So similar to how we've been writing down these general solutions, but using vectors, like I said. Okay. Let's, so instead of describing this in general, I'm going to just do an example that will hopefully be enlightening. So this is, yeah, I don't know. I guess I'll underline this whole title. Okay. So consider the following. We have AX equals 0, where A is the matrix. Wait. It's going to be 1, 0, 0, 1, minus 8, 4, minus 7, 3, like so. Okay. So this system, if we were to write down what it means in terms of the equations involving the variables x1 up to x4, we would get x1 minus 8x3 minus 7x4, right? And then the second row would give us x2 plus 4x3 plus 3x4. And these will both be equal to 0, right? Because the vector will be equal to 0. Sorry, I think I missed something in the chat. Is a vector of variables. Yes, yeah, exactly. Okay, so we would get these two equations, and then our standard procedure for writing down the solution, we would rewrite the first two so x1 and x2 in terms of those free variables x3 and x4, right? So we would take this and we would get two new equations. Well, they're not really new, but we'll just move these to the other side. So x1 equals 8x3 minus 7x4, and x2 equals negative 4x3 minus 3x4, right? Okay. Now, then we would write down, so we have free variables x3 and x4 are free variables, and this is essentially our solution, but like I said, we're going to use vectors to write it down. So how we're going to do this is consider a standard or just an arbitrary vector x, which is going to be made up of the variables, right? So this is a
So there's something
solution.
in the chat.
What's that?
There's something in the chat.
Oh, okay. Let me take a look at that. Sorry. 7x4.
He meant to say like positive instead of
Yeah.
negative.
Yeah. You're right. Thank you. Yes. Okay. So I think we're good from here. Okay, so we're thinking about an arbitrary solution of this system, right? And it would be something of this form. We have x1, x2, x3, x4, right? We know those are the variables. And we also have these expressions over here that describe x1 in terms of x3 and x4, and also x2 in terms of x3 and x4. So what we'll do is just replace x1 with this expression right here. So 8x3, I'll try to make this a little bit neater. 8x3 plus 7x4, right? And then we'll replace x2 with that formula we got for x2. So negative 4x3 minus 3x4, and then we leave the free variables alone, right? Okay, so now you can see that there are some terms here that involve x3 and some terms that involve x4. So we're going to split them into two different vectors, right? So the first one will be everything involving x3. So we have an 8x3 in that first row of this vector. And then negative 4x3, we have just x3, and there's nothing involving x3 in the last entry, right? So we'll just put 0 there. And then plus, this is the part involving x4. So 7x4 minus 3x4, 0, because there's just x3 in that entry, and then x4, right? And then we can factor out that variable, so x3, and then we can write this as just a vector with just scalars in it, right? And then pulling out that x4, we would get 7 minus 3, 0, and 1, right? So now we can see that since x3 and x4 are free, this is just describing linear combinations of these two vectors, right? So now we've taken our solution and written it as a linear combination, right? Okay, so just to make this a little bit more clear, or in my mind, it's a little bit more clear. If we replace these x3 and x4 with s and t, right? So, and if we do that, then we get s times this vector 8 minus 4, 1, 0, plus t times 7 minus 3, 0, 1, where s and t are real numbers. Okay, and the solution set is, of course, just all of So this is just writing this in set notation. And then, like I mentioned before, this is just the span of these two vectors. So in fact, our solution set is equal to the span of these two vectors that we found. Right? Okay. And so it turns out that every homogeneous system, or every, yeah, every homogeneous system has, how did I want to say this? In fact, let me just like word this differently so I don't have to say it awkwardly. Okay, the solution set of any homogeneous system can be written as a span. Right? So a span of vectors. So we can think of it as the solution set as being a span, and remembering what we talked about with the span earlier, it's either going to be a line, a plane, or some higher dimensional set, right? So it kind of limits the types of solution sets that we can get, right? And we kind of already had an idea of the types of solution sets we could get from linear equations, but this just makes it more concrete, even more concrete. Okay.
So
I have
any
a question. Oh, sorry.
Oh,
Go ahead.
so any vector like in this span is like a solution to our system, right?
Yeah, exactly. Yeah. Yeah, so in this case, we have two vectors. So this span is going to form a plane in R4 because that's where our solutions are in R4.
Do we need to do something to indicate that the first vector corresponds to x3 and the second vector corresponds to x4?
No, you don't actually need to.
Okay, cool. Thank you.
Yeah, so it's like at this point when we let we let x3 equals s and x4 equals t, we're kind of like forgetting about the fact that these corresponded to a particular, you know, variable, right? Okay, do the let's see, do 3D interactive things in the textbook work for anyone? Oh, I didn't know there were interactive things in the textbook, but if they do work, that's cool. I don't know. Right, yeah, so there's a nice way of picturing this. I think that there are, if not 3D interactives, then like some pictures in the textbook in this section for you to help visualize this, which is nice. Okay, let's do another example. Okay, so here. So say we have a matrix 1, 0, 2, 1, 3, 2. Now, remember, we're talking about the homogeneous system of equations. So this will be equal to, set equal to 0. So the augmented matrix for this system would be 1, 0, 2, 1, 3, 2 with 0, 0. And if we want to put this in reduced row echelon form, we can, right? So we can take, so we would just need to clear this 2, which occurs in a pivot column. So we would maybe take row 1 goes to row 1 minus 2 row 2. right? So we would get, in this case, the second row stays the same, and the first row will get 0 here, and then -1 and 0. Yeah, okay. Now I'll point out something that you might notice. So when we're doing these types of, when we're doing row operations on an augmented matrix, that looks like this. So we have our matrix A, and then we augment with the 0 vector. That will actually never change. No matter what row operation you do, you'll still get zeros, all zeros in that last column. These will always be 0. So will always be 0. So it's customary when you're solving a homogeneous system like this to not write it as an augmented matrix, to just write the matrix, because the last column will always be zeros. You can write it if you want to, if you just want to be consistent, but again, it won't change. So it's up to you how you want to write it, but I'll probably drop the zeros when dealing with a homogeneous system. If you have a non-homogeneous system, then you should keep that column there because it will change. Let's see. Okay, cool. So this is completely row reduced, right? So it's in reduced row echelon form, and we can write down the, so coming from this matrix, we get that x1, okay, that's x1 minus x3 equals 0, and x2 minus 2x3 equals 0. So x3 being our free variable, we get,
Nate,
yeah,
would that be plus 2x3?
yes, you're right.
Okay.
Yeah.
Cool.
Thank you. Okay, so we have these two equations, and we just follow the same process as before. So writing down our vector, our solution vector, we just replace using these equations that we have for x1 and x2. So we get x3 and -2x3 and leave the last one alone, right? And here we only get one free variable, so we have one vector, and it looks like this, 1 minus 2, 1. And that means that our solution set so maybe I'll make this clear. So our general solution will be t times this vector, where t is a real number, and the solution set will be, I mean, we can write it out in a similar way, but it will just be the span of that one vector. So right. So if we want to visualize this, this is the span of a single vector. That's going to be a line. It will be the line through that vector, right? So it's just a line in R3. So for this particular vector, we get, let's see, if this is x1, x2, x3, then this will be 1, -2, and up 1. So about, I'll try to draw it a little bit better. There we go. Ish. Okay, so a line in R3, this will be your solution set. Okay. Okay, so we can also do a similar thing with non-homogeneous systems. So we can also use vectors to write down the solution set. So just to be clear, a non-homogeneous system is just a system AX equals B, where B is not equal to 0, right? So anything that is not homogeneous is non-homogeneous, right? So let's look at an example to see the process. So consider the system AX equals B, where our matrix is 1, 2, -3, -6, and B is going to be -3, -6, like that. Okay, so we can write down the augmented matrix, and that will be this guy right here. So notice that, oh, yeah, okay, wrote it down correctly. Notice that the second row is a constant multiple of the first row. And if you ever see something like that, what will happen is one of the rows will go away, right? So we can actually write down what the row operation would be, but it's good to know that if you see a row that is a constant multiple of another, you can just write all zeros in for that row. Okay, so the row operation would be, we would take row 2 and replace it with row 2 minus 2 times row 1. And if we do that, we'll see that we'll get 0, 0, 0, right? Okay, so we get one equation out of this, which is x1 minus 3 times x2 equals -3, right? So writing x1 in terms of x2, we get -3, oops. Yeah, plus 3x2. Okay. And we use the same process. So here we have our solution. Use this equation to replace x1. And then here we can split this into two vectors, one containing those terms with x2 in them and the other containing the constant terms. So here we would get -3, 0 plus the vector containing the terms involving x2. And again, we'll factor out that x2 so that we can write it like this. Right? Okay. So that means that our solution set is going to be the set like this, such that T is in R. Now, this is not all linear combinations of some certain collection of vectors, right? It is, but it is, how we can see it is a span. So this part represents a span, like the other examples that we saw, but then it is translated. So the entire span is translated by this vector minus 3, 0.
Okay, so like when we like find the solution like and write it in vector form, we don't have to write it using span.
Yeah, so you can't necessarily do that for a non-homogeneous system. You can for a homogeneous system, but if you want to write down the solution set for a non-homogeneous system, this is probably how you should write it. Another way of writing it would be, but this is kind of an abusive notation, so I wouldn't suggest it. You could write it this span plus this vector, but yeah, I wouldn't, just don't do this actually. Just to be, actually correct with our notation. But that is how you can think of it though. So you take the span and you translate everything by that vector minus 3, 0. So if we wanted to picture this, right, this is in R2, our solution set for this part. So we have the span of 3, 1, right? 1, 2, 3, and up 1. So it would look like this. And then we translate that entire thing over by, so it would be over 3 and up 0. So just over 3. There's 1, 2, 3. And this is the solution set. Of the non-homogeneous system. Okay. And then the general solution is your minus 3, 0 plus t times 3, 1, right? And what is actually the case is that this part, this portion, is the solution of the homogeneous equation that you could create by just replacing b with the 0 vector. So by this I mean actually this equation. So our, oops, my goodness. Our A was 1, 2, minus 3, minus 6. So here, this is the solution of 2 times x equals 0. Right? This is, okay, I'll write that down in a second. But this is what we will call the homogeneous solution because it is the solution of a homogeneous equation. And then the other part is called the particular solution. Okay, and I'll write this out for the general case, but this is just in terms of this example. We have the particular solution and then we have this homogeneous solution. So I should write this. Called the particular solution. This is called the homogeneous. And so the solution of the non-homogeneous problem or the system is the particular solution plus homogeneous solution, right? Okay, so if you have already taken differential equations, you may see something familiar going on here. So when you talk about homogeneous differential equations, you talk about particular solutions plus homogeneous solutions, and it's the same kind of idea going on. Yeah, exactly. General solution equals particular plus general homogeneous. Yes. Okay, so if you haven't had differential equations yet or don't even plan to, that's fine. This is this in this context. Okay, so just to write this out in terms of a general system. So given a non-homogeneous system, AX equals B, the associated homogeneous system is just where you set it equal instead to 0, right? Same matrix A, right? And the homogeneous wait, sorry, I can't read my own notes. Let's see. Okay, this is the associated homogeneous system. And then if a non-homogeneous equation is consistent, assuming it's consistent and it has a solution, it will be of the form. So its solutions so we can always write it like this, where we have our particular solution plus the homogeneous solution, which can be written as a linear combination of vectors like this, right? Where these t's are just constants, right? So let's go like this. So here, this is the particular solution. And then this whole portion is your homogeneous solution, which is the solution of the associated homogeneous system. Okay, so it breaks into two pieces like that. Okay. Are there any questions at this point? Is everything?
A question.
Yeah.
Does anything happen if like the homogeneous system has a solution, but the non-homogeneous system doesn't?
Right. In that case, then you don't get a solution of this form. So if you have if A equals B is inconsistent, that will mean that there's no particular solution. I'll just write it this way. Means no particular solution. And it may be the case that, well, it's always the case that the homogeneous system is consistent, right? So it might have a bunch of solutions, but if you have no particular solution, you get no solutions of the homogeneous equation, even though you could write down the homogeneous solutions. Hopefully I said that in a way that made sense.
So even though the homogeneous system itself has solutions, you cannot take the homogeneous solution and apply it to the inconsistent non-homogeneous system.
Yeah.
Ooh, words.
I know. It can get difficult. But yeah, so no particular solution means You're inconsistent means you don't get a solution of this form right here. Okay. So let's see how we're doing on time. I wanted to give you guys how much time to do the quiz? I guess like 20 minutes. So someone stopped me at 1:30. Okay, because if I don't stop myself. Okay, so we get to move on to section 1.7. So this is on linear independence. Right? And this is a pretty important concept in linear algebra. So the definition might seem a little strange. It's actually easier to state the definition of linear dependence. So I'm going to do that first. So definition. So this is a property of a collection of vectors. So a set, oops. Let's see. Set of vectors, say V1 up to Vk in Rn. This is said to be linearly dependent, right, if there exist scalars, so x1 up to xk in R such that I'll have to put this on the next page. So yeah, such that we can write this as a linear combination x1, oops, x2, v2 to xk, vk. This is equal to 0. Okay. So this is said to be linearly dependent if we can find these scalars, x1 up to xk. So this is just saying that we can find a solution of this vector equation, right? So another way of thinking about it, because this is a vector equation. So what this means, yes. So that's an important point. There exists x1 up to xk, not all 0. So at least one non-zero, such that we get this relation. Yeah, because we could always take them all to be 0. We want some non-trivial combination, right? Okay. And if this is the case, what this means, so how we can interpret this is that we can write one of the vectors vi, so one of the vi's as a linear combination of the others. Right? Okay. And we would do so using this equation that we would have found, right? And this is called a linear dependence equation. Because it tells us how these vectors depend on one another, right? Okay. So that is what it means to be linearly dependent. And the opposite of that is linear independence, right? So second definition, this is also a property of a set of vectors. So a set of vectors v1 up to vk in Rn is said to be linearly independent I mean, we could just say it's linearly independent if it's not linearly dependent, but let's be a little bit more specific than that. So linearly independent if this equation, so same equation as before, so x1 up to xk bk equals 0 has only the trivial solution. Meaning x equals the 0 vector, right? Okay, let me write this out. So this means x equals the 0 vector, or all of these to xk are equal to 0. That's saying the same thing. Okay, so this is what it means to be linearly independent. And the way that we've stated it, we can see that it's just asking for solutions of this vector equation, right? So we can approach this in the same way that we've been solving linear systems, because we get a linear system in terms of a vector equation. We know that we can, that's just one way of representing that linear system. We can translate it into something in terms of a matrix and then solve that. And that will tell us whether we have linear dependence or linear independence, right? Okay, so I still have a little time, so let's do one example. Okay, so say we have a collection of vectors in R3. So 1, 1, 1, 1, minus 1, 2, and 3, 1, 4. So the question is this set linearly dependent or independent? And so we're asking whether the equation x1 times the first vector, x2 times the second vector, and x3 times the third one equals 0. Well, might as well write out the vectors. So. Whether this has a non-trivial solution, right? So we just solved the system, right? So we can form a matrix out of the vectors. This is a homogeneous system, so we don't need to write down the augmented part of this matrix, right? Because we'll just have all zeros on that side. So we can just take this and row reduce, right? So I'm going to do this a little bit faster than I normally would. So I'm going to take row 1, or sorry, no, row 2. To row 2 minus row 1, and I'm going to actually do two things at once. So also take row 3 to row 3 minus row 1. So row 1 stays the same. Row 2 becomes 0, -2, -2. And this last one becomes 0, 1, and 1. Right. And then we can see that the third row is a constant multiple of the second row, so it actually will disappear. We get 1, 1, 3, and then dividing by -2, we'll get just ones there. Okay, so I did that kind of fast. If you want to, you can double check by doing it yourself. But what we get here is, this is in row echelon form, not reduced, but that's fine. What we can see is that we have a free variable, right? So we can see from this. Okay, and what that means is that we have a non-trivial solution. And this is that fact that we had way at the beginning. So I'll scroll all the way back. This was like the first thing that we talked about here. This homogeneous system has a non-trivial solution if and only if the equation has at least one free variable. So I'm using that fact, right? This has this example, we row reduced, saw that we have a free variable. That means that we have a non-trivial solution. Right?
So does that mean that these vectors are linearly dependent?
Yes, exactly. So non-trivial solution means that we have linear dependence. If we have only the trivial solution, then we have linear independence. So this is, the vectors are linearly dependent. Okay, so I realized I forgot to upload the quiz to Canvas. So I'm going to do that right now. But while you're sitting here, I'll give you this exercise. So for this problem, try to find a linear dependence relationship. Is that what I called it? Relationship? Equation. For this example. Okay, so we know they're linearly dependent. So go ahead and try to write them as a linear dependence equation.